So now we're going to turn our attention from vertex form to this ax squared plus bx plus c form of a quadratic function. Sometimes we work with quadratic functions that are written in vertex form. However, you can also transform it into an equivalent format, which is this one. And each format has its own benefits and drawbacks. When you're working with a quadratic equation, f of x equals ax squared plus bx plus c, the axis of symmetry is always located at the line x equals negative b divided by 2a. A, b, and c are all going to just be constants. So you would plug those constants into this formula, and you would know where the axis of symmetry is without having to graph it. The vertex looks a little complicated, but all this is saying is take whatever you found as the axis of symmetry, whatever number that is. Remember that the vertex shares that x coordinate, and substitute that x coordinate to find the corresponding y coordinate of the vertex. We'll do an example. And just like vertex form, if a is greater than 0, the parabola will open up. If a is less than 0, the parabola opens down. Before we look at some MyMathLab examples, we need to pause and review some skills that you should have. A parabola models the path of a ball like you see here when it is bouncing and under the influence of gravity. Knowing when the position of the ball is 0 tells you important information. It tells you at what times the ball is in contact with the ground. Okay, so we need to review how to find the roots, which are also called X-intercepts or zeros of a quadratic equation. The first method you should know, but we will review, is you should try to factor. When you want to find the roots, you always let y equal 0. So I've replaced my f of x with a y, two different names for the output, and I'm now going to substitute y equals 0. This gives me this equation. Now, I can't just try to get x by itself. Since there's multiple terms with x's, that's going to be a problem. Instead, I can factor. And the method of factoring I would use here is known as Gcf, greatest common factor. When you factor by greatest common factor, you look for what the two terms, in this case the 3x and the 6x squared, have in common. 3 and 6 are both divisible by 3. I put that in my common factor. X and x squared, what they have in common is an x. It would not be appropriate to say they have x squared in common, because while this term does have an x squared, this one falls short by an x. So 3x is my GCF. Once you have your GCF, you think about the distributive property and how you would get back your original expression. 3x times what would stay 3x? It has to be a 1. Plus 3x times what would become 6x squared? Well, I need a 2 to form the 6. 3 times 2 is 6. And x times another x would become x squared. I take 3x and I set that factor equal to 0. And I do the same thing on the right, because I know that if I multiply two quantities together and they equal 0, the only way that can happen is if, in fact, one of those quantities equals 0. Then you would solve each new equation you've created. I just use regular solving techniques, and I found that I actually would have, in this case, 2 x-intercepts. Now, GCF factoring should be the first thing you try when you try to factor, but it's not always going to work. Take the next quadratic, for example. I'm going to set it equal to 0. Now, this is a 3-term polynomial. We call that a trinomial. When I look for what's in common to all 3 terms, I don't find anything. 2 of my terms have x's, but the other one doesn't. There's nothing that all the coefficients are divisible by, so GCF is not going to work. So there's another method, and different people have different names for it. A lot of people refer to it as the add and multiply method. This method is particularly helpful when working with trinomials. And how this method works is you are always looking to find a pair of numbers that will add up, those same two numbers will multiply to give you the constant term. It always goes in that order. It's usually easiest to start with the multiplication list. You just make a list of numbers that you could multiply to get -6. You continue making that list. And as you make it, you now check in with this middle box, the A or add to box. My pair of numbers which will correctly factor this trinomial will add up to -5. And as I go down my list looking for what adds up to -5, I find this is the only pair of numbers that does the job. Whenever you factor by this trinomial A and M method, the setup is always the same. You create two sets of parentheses, and if x squared is your first term, you will put x and x in the front of each one because x times x is x squared. Then you take the numbers from your list, a +1, so hook it on in the first set of parentheses with a +1, and a -6, hook it on to the x in the second set of parentheses. The order of the parentheses doesn't matter. Now we would proceed the same way we did in the last example. Once we have our factors, set them equal to 0, and solve. This quadratic also has two x-intercepts. One of them is the point -1, 0. The other one is the point 6, 0. Now, you may or may not remember how to factor, and you may or may not be any good at it. There is a second method that will always work, but it tends to require more work. Suppose I was trying to find the x-intercepts for this quadratic. I begin again by putting 0 on the left-hand side. Maybe I just never was any good at factoring, and I want to use a method that will just always get me the right answer. This method, the quadratic formula, is based on knowing the ax squared plus bx plus c form of a quadratic. You always find the a term as the coefficient on the x squared, the b is the coefficient on the x term, and the c is always the constant term. Notice I don't have a coefficient on my x squared term, so it would be appropriate to say there is one of them. In other words, make a equal to 1. The quadratic formula is just that. It's a formula. Inside the box is the quadratic formula. To use it, you simply have to substitute the values of a, b, and c into the proper locations in the formula. We would leave the x equals there. B is -5. Now I'm supposed to substitute that into -b. So there's a negative from the formula, and the b value is -5. So notice how I've substituted that. All over, big division bar, 2 times a. And I can go back and add a little bit of coloring to that just to show you. So my a value is 1, goes here and here in the formula. My b value is -5, and that's going to go here and here. And my c value is 3, and only is used once in the formula. Now all that's left is to do some simplifying and some calculating. So you want to look at each of the main chunks that you have here. The -5 minus a -5 is the same as just a +5. Keep the plus and minus sign. Underneath the square root, we have 25 minus 4 times 1 times 3, which is 12. All over 2 times 1 is 2. I can further simplify under the square root, which brings me to 5 plus or minus square root of 13 over 2. Now we need to deal with that plus minus symbol. I'm being told that x can equal 5 plus the square root of 13 over 2, or x can equal 5 minus the square root of 13 over 2. And again, you've seen many cases now where quadratic equations actually do have multiple roots. The last thing you would do at this point is go to a calculator to type in these expressions and get their decimal equivalents if needed. Certainly, if I was going to graph, I'd want an approximate value for that. So I go ahead and type the values into a calculator and I can see their decimal equivalents. I've taken those decimals and just rounded them to the nearest tenth. Notice my x-intercepts are both positive in this case. They can be both positive, both negative, or one of each. This was just a short introduction. If you feel like you need more review, there are plenty of videos on how to factor and how to use quadratic formula. Do a little practice if that's what you need. All right, this MyMathLab problem is going to look very similar to the ones that you worked on in part 1. The key difference you want to notice is that the format of the quadratic equation has changed and no longer looks like vertex form. In fact, it looks more like our ax squared plus bx plus c form. When you look at the given quadratic, the x squared term is sitting in the middle. So I need to be careful here and make sure when I'm identifying my a, b, and c, I remember a is always in front of x squared, b is always in front of x, and c is the constant. So in this particular example, the number in front of the x squared, well, I just have a minus sign. Remember, that's really a negative 1. So my a value is negative 1. My b value, I need to look for the term that has the x and look at what's in front of it. Here's the x, in front is 4. So b is 4. And c is the constant term without any variables, which is 12. Now that I know my a, b, and c values, I can proceed with finding the vertex and the intercepts. To find the vertex, you do a two-step process. First, you find the equation for the axis of symmetry. And you do that using the formula x equals negative b over 2a. I substitute my b value, which is 4, but don't lose track of that negative, over 2 times a, 2 times negative 1. My numerator is negative 4, my denominator is negative 2, and that equals 2. So on my way to finding the vertex, I've actually answered this first question. The axis of symmetry is. But do not just put 2 there. It's an equation. It has to have an equal sign. And because it's a vertical line, it's always x equals. So my axis of symmetry is x equals 2. The second step towards finding the vertex is to substitute x equals 2 into the original equation. Substitute 2 for the x's. Order of operations is I do the exponent first, which means I take 2 and square it, which is 4. Now I do the multiplication and finish. Putting those two steps together, my vertex coordinate would be the point 2, 16. All right, now I need intercepts because I need some other points in order to be able to graph. The easiest intercept to find is always going to be the y-intercept. Here's why. To find the y-intercept, you substitute x equals 0 into your original equation. Notice what happens. 0 times anything is 0. This is also 0. And you're only left with the c value, and that will always happen. It turns out that the c value is in fact going to be your y-intercept for any quadratic, not for other kinds of functions. So I have the point 0, 12. And in MyMathLab, you would begin by clicking on the vertex, which would be 2, 16. You would continue by clicking on the y-intercept, which goes on the y-axis here. And then you're going to see it open up the parabola for you. In this case, the y-intercept is enough to get the graph. If I had to locate the x-intercepts, as you saw earlier in this video, that means that you would be taking and substituting 0 where the y is, which would give you the equation 0 equals 4x minus x squared plus 12. In order to be able to find the roots, you would need to do the quadratic formula. So if you want practice, this is a good one to practice with. And in case you do decide to practice, the values you should get are x equals 6 and x equals -2. I apologize for the slight inaccuracy on my graph. Answering the remaining questions, the domain of the function, I attempt to name the lowest and highest x values. I can't do that with quadratic equations, so they're always going to have a domain of -infinity to +infinity. And for the range, I try to name the lowest value, but there's arrows. So my lowest value will be -infinity up to my highest value, which is going to occur at the vertex. And that's at y equals 16, and we do equal 16, so square bracket on the right. One thing we haven't tied in from previous lessons yet is the fact that this point on the parabola, which we call the vertex, in this instance turns out to be not just a vertex, but a relative maximum. It's the largest y value that occurs on this graph. That information allows us to attack problems like this. It says, consider this quadratic function. It has an x squared, it's going to be quadratic. But determine without graphing whether the function has a minimum value or a maximum value. I can determine the answer if I can figure out if my parabola smiles or frowns. And remember, it's the a value that gives me that information. My a value is 7. That's a positive number. And when it's a positive number, I know my parabola is going to smile. Just by looking at this picture now, I can tell, well, the vertex would be here. Is that the highest or the lowest y value on this graph? It's at the bottom, so it's a minimum value. So just by knowing the a value, I know whether this quadratic will have a maximum or a minimum value. Now it says it wants me to find the value and determine where it occurs. When it says find the value, that's the y coordinate. When it says where it occurs, that's the x coordinate. So I need the x and y coordinate of the vertex. I can do this without graphing. We saw in the last example that when you want to find the coordinates of a vertex without a graph, there are 2 steps. You begin with the formula x equals -b over 2a. I already identified a in my quadratic. My b value is -7. And if I needed the c value, c would be 0 because it does not exist there. So I have x equals -7 all over 2 times a, 2 times 7. That gives me an x coordinate of +7 over 14, or in other words, the fraction 1/2. Now I take 1/2, substitute it into my function. And if you're not particularly fraction friendly, you can use a calculator to evaluate this expression. From my work, I know that the minimum value is -7 over 14, and it occurs at the x value, x equals +1/2. Since this is a quadratic function, the domain will be -infinity to +infinity. And I can determine the range by looking at my sketch at the top. Since the vertex is a minimum, its y-coordinate is the lowest point on the graph and the smallest value in the range. So the range begins with -7/4, square bracket, and I can't name the highest y value because it keeps going.